Let's consider the coffee example. A medical researcher observes that people experience an increase in blood pressure after consuming coffee. Elevated blood pressure is a temporary side effect of caffeine. Coffee contains caffeine, a compound that stimulates the nervous system. After analyzing past medical studies, the researcher infers that increased blood pressure seems to increase the risk of heart disease. She wonders if heavy coffee drinkers face the same risk because of regular spikes in blood pressure caused by caffeine. Let's consider the coffee example. A medical researcher observes that people experience an increase in blood pressure after. Ask questions. Observations and inferences often prompt questions, which will help narrow the focus of an inquiry. The more you ask, the more you learn. Science enables us to answer empirical or practical questions. Empirical questions require quantitative data and qualitative data for their answers. Quantitative data is measurable. Some examples of quantitative data are the area of a football field or the weight of a box. Qualitative data is something that can't be measured but can change over time. For example, the color of the sky or the texture of coffee grounds when they're dry versus wet are both qualitative data. Scientific inquiry, however, can't answer questions about a person's beliefs, ethics, opinions, and feelings. Here are some examples of empirical questions that science can answer. Does a drop in temperature affect the number of offspring that Now let's explore how the medical researcher framed the question to proceed with her scientific investigation. She wrote down the question, are coffee drinkers more likely to develop heart disease in their lifetime than non-coffee drinkers? She can try to answer this question using both quantitative data and qualitative data. The quantitative data will include blood pressure readings of people who drink coffee to compare with those of people who don't drink coffee. The qualitative data will consist of computer images of the heart. The researcher will compare the changes in the images over time. However, these questions can't be answered with quantitative data or qualitative data. How do regular coffee drinkers feel about their daily coffee consumption? Are coffee drinkers worried about their heart disease risk? Are coffee manufacturers responsible for warning people about the risks of caffeine? Construct hypotheses and predictions. After the question is framed, it needs to be answered. Scientific researchers consider all possible answers to the question when forming a hypothesis. A plausible explanation Now the researcher must form a hypothesis for the question she put forth. Are coffee drinkers more likely to develop heart disease in their lifetime than non-coffee drinkers? Based on the information she has gathered, the researcher may develop a hypothesis such as this one. Drinking more than 5 cups of coffee a day increases blood pressure, causing an increase in heart disease across the lifespan. Using this hypothesis, the researcher predicts that her study will show that heart disease is more common among heavy coffee drinkers than among non-coffee drinkers. Test the hypothesis. The next step is designing an experiment to test the accuracy of the hypothesis. Experiments usually involve several variables that must be identified and analyzed. These factors change an experiment. For example, the coffee researcher wants to study the effect of caffeine on the health of the heart. In this case, the amount of caffeine, blood pressure, and the risk of heart disease are variables. An experiment usually has 2 kinds of variables. In the coffee example, the researcher wants to study 2 groups of people: heavy coffee drinkers who drink 5 or more cups of coffee a day, and people who don't. In the coffee example, the researcher wants to study 2 groups of people: heavy coffee drinkers who drink 5 or more cups of coffee a day, and people who don't drink coffee. She wants to study them for 15 years and monitor their risk for heart disease. The researcher implements these factors to strengthen her study. She starts with a large sample size of 10,000 people. She chooses people in the same age group. These people have no current medical issues and have a healthy body weight. Age and body weight are known risk factors for heart disease, so these choices control these factors. She further divides the people into male and female subgroups to control differences in gender. She interviews the participants to learn more about their past and their family medical history. She rejects people with a family history or a personal history of heart disease because they have an increased risk of heart ailments regardless of coffee consumption. At the start of the experiment, she screens both groups to test their blood pressure and carries out imaging of their heart and circulatory systems. She decides to repeat these tests every year for 15 years. When conducting studies in medical research, it's important to note that some factors can't be controlled. In the case of human subjects, certain factors can't be regulated because of time, cost, or even ethical considerations. The coffee researcher conducts interviews to learn the medical history of the participants and their families. The participants may or may not provide accurate information. The information can be verified by checking their medical records, but the researcher needs the participants' permission to check their records. This process can be time-consuming and costly, so she chooses not to do it for the experiment. The researcher considered factors such as age, gender, and weight for the study. However, she didn't take into account other factors such as smoking habits and diet that can increase the risk of heart disease. Considering all of the factors would lead to a decrease in sample size. Repeat or retest. Repeating a trial reduces the possibility of errors. In fact, the entire set of experiments should be repeated by other scientists to check the accuracy of the results. When repeated experimentation supports a hypothesis over a long period of time, it can become a scientific theory. Some people have a misconception that theories turn into laws after extensive research. A scientific law is a scientifically acknowledged principle that's been confirmed by In some cases, repeated trials with the same group aren't possible. For example, in the coffee researchers' study, the subjects will age 15 years by the time the study ends. However, the researcher can repeat the study with a different population in other locations around the country to see if she gets similar results. Analyze the results and make a conclusion. After finishing an experiment, the next step is to analyze the results and develop a conclusion. During this step, scientists create further hypotheses, analyze the data, and establish conclusions. They organize data neatly into graphs, tables, and charts. Other scientists can review these results and verify them. The conclusions drawn should answer these questions. Do the results support the hypotheses? What happened in the In the coffee experiment, the researcher established that there was no significant difference in heart disease risk between coffee drinkers and non-coffee.
Many farmers and gardeners compost their plant and animal waste. Many farmers and gardeners compost their plant and animal waste. Many farmers and gardeners compost their plant and animal waste. The living material Many farmers and gardeners compost their plant and animal waste. The living material naturally decays in compost bins, forming a dirt-like substance that's rich in nutrients. The next season, farmers use this substance as a natural fertilizer for their crops. A biology student has grown tomato plants for several years. Until now, he used an artificial fertilizer formulated for tomato plants. This fertilizer caused his plants to grow faster and taller than they grew in unfertilized soil. The student wants to know whether using natural compost will cause his tomato plants to grow faster and taller than his artificial fertilizer. Answer the following questions to plan an investigation using the steps of the scientific
Atoms and elements. Anything that occupies space and possesses mass is matter. Atoms are the basic units of matter. In the 5th century BC, Greek philosophers Leucippus and Democritus put forward the theory that matter is made up of tiny particles that cannot be divided further. Let's explore the particles in an atom. Protons. Protons are positively charged particles. They are located in the nucleus. Electrons. Electrons are negatively charged particles. They move around the nucleus in orbits with specific energy.
A substance made up of only one type of atom is called an element. An element
The table arranges the elements in increasing order of atomic number. The periodic table provides information about the protons and neutrons that make up the nucleus of a specific atom. Protons. The atomic number tells us the number of protons in the nucleus of an atom. Atoms of any element have a fixed number of protons. In fact, knowing the number of protons helps us identify the atom. For example, carbon has 6 protons, so its atomic number is 6. Neutrons. Isotopes are atoms of the same element that have different numbers of neutrons. Average atomic mass is the average mass of all naturally occurring isotopes of an element based on their abundance. This means that the most common isotopes are factored more heavily into the calculation of average atomic mass than the least abundant isotopes. Mass number does not appear on the periodic table. It is the sum of the number of protons and the number of neutrons in an atom. Select the correct answer. The first model represents the proton and neutron distribution in the nucleus of 4 helium isotopes. The second image shows the entry for helium in the periodic table. Based on the information in the periodic table, which is the most common isotope of helium? A, B, C, D. Molecules and compounds. When two or more atoms group together by means of a chemical bond, they form a molecule. Molecules may consist of atoms of the same element, known as any elemental molecule, or they may consist of several different elements. Compounds are molecules that form when 2 or more elements bond together. For example, water, H2O, is a compound because it is made up of 2 hydrogen atoms and 1 oxygen atom. Therefore, all compounds are molecules, but not all molecules are compounds. Types of chemical bonds. 2 or more substances need to combine to form a molecule or compound. The force or attraction that holds these substances together is called a chemical bond. Let's learn about the 2 most important chemical bonds: covalent and ionic. Covalent bond. A covalent bond forms when atoms share electrons in their outer energy levels or shells. In an atom, the first electron shell can hold up to 2 electrons. Shells 2 and 3 can each hold 8 electrons. A hydrogen, H, atom has only 1 electron, but its shell can hold 2 electrons. Oxygen has 8 total electrons, 2 on its inner shell and 6 on its outer. Ionic bond. Atoms have an overall neutral charge. An atom needs to have its outermost energy level completely filled or completely empty to acquire stability. To do so, atoms either gain or lose electrons. An atom becomes an ion when either losing or gaining 1 or more electrons. Let's consider the example of sodium chloride, NaCl, commonly called table salt. Sodium has just 1 electron in its outermost energy level. It can acquire stability by giving up this one electron. When it loses this electron, it becomes a positively charged sodium ion, Na+. Meanwhile, chlorine has 7 electrons in its outermost shell and needs just 1 electron to fill it and become more stable. So it readily accepts an electron from an atom such as sodium and becomes a negatively charged chloride, Cl- ion. These two oppositely charged ions attract each other, thus forming an ionic bond. Chemical reactions. A chemical reaction is a process that involves the rearrangement of atoms or a group of atoms to form new substances. This rearrangement requires the breaking up of existing bonds and the forming of new ones. For example, when iron, Fe, reacts with oxygen, O2, in the air, it forms rust, Fe2O3. At the start of a reaction, most chemical reactions need some input energy to begin. For example, striking a match on the side of a matchbox ignites the match. The minimum amount of input energy needed for a reaction to occur is called activation energy. The lower the activation energy, the faster the reaction occurs. Chemical bonds can be broken when molecules are in a contorted state, called a transition state. Activation energy is required to get the reactant molecules into a transition state. So, striking a match provides